Good evening, all of you. So this is the session 4. So as you know that in this session we used to solve the GATE previous year questions. So we will begin with our first question. So this is the GATE 2021 question that came in set 1. So in this question they have given the 4 options and they are asking which one of the following is correct. We will read one by one and then we will answer accordingly. In the first option they are telling the partial treated effluent from the food processing industry containing high concentration of biodegradable organics is being discharged into the flowing river at a point P. If the rate of degradation of the organics is higher than the rate of aeration, then the dissolved oxygen of the river will be lowest at the point P. So in this thing they are telling, so if the in the pre-treated, partially treated effluent of a food processing factory is being discharged at the point P. Suppose this is a point P and it is being discharged. So they are telling then the dissolved oxygen level of the river will be lowest at this point. However, based on our theories, always the dissolved oxygen of the river will be lowest at the certain distance from the upstream. That is, it will be lowest at the certain point in the downstream, not at the point where the water will fall. So obviously this is incorrect. Second is the most important type of species involved in the degradation of the organic matter. In the case of activated sludge process based wastewater treatment is chemoheterotroph. Chemoheterotroph they are talking. Chemoheterotroph basically are the microorganisms which uses organic matter as energy source and carbon source. Okay, so remember this chemoheterotroph. Chemoheterotroph, these are the organisms which uses organic matter as energy source and carbon source. Now moving to the C point. I think someone has. Now the third point says the for the effluent sample of a sewage treatment plant, the ratio of BOD 5-day upon ultimate BOD is more than 1. But this C section is incorrect because we know BOD of at 5-day is around 68% of the ultimate BOD. 68% of the ultimate BOD. Ultimate BOD. So obviously BOD 5 by BOD ultimate cannot be greater than 1. So this is incorrect. Other thing is the last option is the young lake characterized by the low nutrient content and low plant productivity is called eutrophic lake. So based on the level of productivity and the nutrient content, the lakes are categorized as oligotrophic, then comes mesotrophic. This is the increasing order of productivity. Increasing order of lake productivity and productivity product just increasing order of lake productivity and nutrient sources. Lake productivity and nutrient level and nutrients level. So first comes oligotrophic, second comes mesotrophic, third comes eutrophic, fourth comes senescent. So based on the increasing order of the lake productivity and nutrient level, the lakes are categorized as oligotrophic, mesotrophic. This is an increasing order. Means in case of maximum lake productivity and nutrient level will be found in senescent. where after that it will be neutrophic, then mesotrophic. The lowest productivity and the nutrient level will be in oligotrophic. But in the question they have asked, in the question they have mentioned that the young lake characterized by the low nutrient content and the low plant productivity is eutrophic, but it is not the eutrophic, it will be oligotrophic. So as I just mentioned, based on the increasing order of lake productivity and nutrient level, lakes are categorized into oligotrophic, mesotrophic, eutrophic, and senescent. So oligotrophic will have the lowest lake productivity and the nutrient level. So among the all the options, option B will be correct. I hope it is clear. Question number 1 is clear to everyone. I am moving forward to the second question. In second question, they are mentioned the bag filter has to treat 12 meter cube per second of waste gas continuously. The bag house is to be divided into 5 sections. So it is a 12 meter cube of waste gas continuously. The bag house is divided into 5 sections of equal closed area, such that one section can be shut down for cleaning or repairing. Kindly note this point. One section can be shut down for cleaning or repairing while the other 4 sections continue to operate. And so they are telling a bag house filter has to treat a particular amount of waste gas continuously, and bag house has to be divided into 5 sections having equal cloth area, in which one section will be shut down for repairing and cleaning while other 4 sections will be used for operation. An air to cloth ratio of 6 meter cube per minute meter square cloth will provide sufficient treatment to the gas. The individual gas bags are of 32 centimeter in diameter and 5 centimeter in length. The total number of bags required in the bag house is, so they are, the information they have provided the flow rate of the gas, then they have given the area to cloth ratio, and the second number of sections, and up in number of sections one section will be for one section will be shut down and remaining 4 section will be in operational mode. And they have given that the individual bags are of 32. The dimensions of the individual bags are also mentioned, and now they are asking the total number of bags required for the bag house. So looking at the data, we will progress. Now let's, so first they have mentioned the flow rate of the waste gas. So flow rate is 12 meter cube per second. Second thing, they have mentioned the bag house divided into 5 sections. Okay, fine. Here they have mentioned an air to cloth ratio of 6 meter cube per minute meter square cloth. Please notice the unit they have given. So air to cloth ratio. Air to cloth ratio is 6 meter cube. 6 meter cube per minute per meter square cloth. This is what they have mentioned. 6 meter cube per minute per meter square cloth. So here is this. Okay. So can it, so 6 meter cube per minute per meter square cloth. So we can write it as 6 meter per minute. Meter cube by will get cancelled by meter square and meter per minute. Then we can write it as 6 meter per 60 seconds. 1 minute is 60 seconds. So we can write like this also. So now so air to cloth ratio. Now we will move area of the cloth. First we will find out area of cloth. Area of cloth will be flow of air divided by air to cloth ratio. Flow of air by air to cloth ratio. Now flow of air is given as 12 meter cube per second divided by, now area of cloth, how I will know that I have to calculate the area of the cloth? They have given the dimensions of the cloth. obviously I have to, so see here in this last line, second last line, the individual bags are of 32 centimeter in diameter and 5 meter in length. So individual size dimensions they have given. So if I get to know the total area of the cloth, then we can easily find out the number of bags required. And look at the unit here, meter cube per minute meter square. Now here, after air to cloth ratio, after this the unit is meter cube per 60 seconds. Flow rate is meter cube per second. So from here we can get the area of the cloth, meter square. So meter cube per second divided by 6 meter per 60 second. 6 meter per 60 second. So we can write it like this: 12 into 60 divided by 6 will be meter square. Second will get cancelled. Meter cube will get cancelled by meter. So now the value will come out to be 6 120 meter square. 120 meter square will be the value. Area of the cloth. Area of cloth. 120 meter square will be the value. Now, knowing the area of the cloth, we have to calculate the surface area of each bag. Individual bag they have given. We have calculated the area of the cloth. Surface area of the bag is yet to be calculated. For surface area of cloth, surface area of bag, surface area of bag. The individual bags are of 32 centimeter in diameter and 5 meter in length. Since they are mentioned in diameter and length, it will be cylindrical. Surface area of cylinder will be 2 pi RL, where 2 into 3.14 into radius diameter they have already mentioned 32 centimeter, so it will be 32 centimeter. So for meter it will be 16 centimeter. For meter it will be 0.16 meter into length they have mentioned as 5 meter. So total value will come out if you calculate 3.14 into 0.16 to 5 multiplied by 2, it will be 5.024 meter square. Now this is the surface area of bag. From surface area of bag, here they have given the size of the individual bag. From there we have calculated surface area of bag. So number of bag required. Number of bag. This is the surface area of bag. Here we have already calculated the area of cloth, 120 meter square. So 120 divided by 5, this surface area of bag will give us around 23.88 bags, which is quite equivalent to 24 bags. So I hope it is clear till now. So it is equal to 24 bags. Now in the question they have mentioned that there the bag house is divided into 5 sections of equal cloth area such that the one section can be shut down for cleaning and or repairing while the 4 section can continue to operate. Since bag house is divided into 5 sections, bag house is divided into 5 sections of equal cloth area, and in that one section is shut down while 4 sections are operational mode. So therefore minimum number of bags required will be minimum number of bags required based on the section. So 24 bags divided by 4. So this will be 6 bags. So minimum number of bags required is 6 bags. So the total number of bags, this is in operation, but total number of bags So total number of bags, how much it will be? Number of sections into bag per section. Bags per section. So it will be 5 into 6, 30. 30 bags. Is it clear to everyone? Is it clear? Okay. So I hope it is clear. So now I will move to the second question. Sorry, this is the third question. So in the third question, they have mentioned a secondary clarifier handles a total flow of 9600 meter cube per day. So total flow they have given from the aeration tank of conventional activated. The concentration of the solids in the flow of aeration tank is 3000 milligram per liter. The clarifier is required to thicken the solid to 12,000 milligram per liter. Hence, it is to be designed for a solid flux of 3.2 kg per meter square per hour. The surface area of designed clarifier thickening is in meter square in integer is. So, how we will solve this question? Now, first we need to see the data, and in that they have mentioned the design for a solid flux of solution. So, in that design solid flux is design design solid flux is 3.2 kg per meter square hour. So design flux is 3.2 kg per meter square per hour. Now total flow from to the secondary clarifier from the aeration tank is total flow. Total flow to secondary clarifier is 9600 meter cube per day. We can write it as 9600 meter cube per 24 hour. So here we will get 400 meter cube per hour. So total clarifier, this is total flow to secondary clarifier is 9600 meter cube per day as mentioned in the question. So in terms of meter cube per hour, it will be 400 meter cube per hour. Now this is MLSS, also concentration is given. The clarifier is required to thicken the flux 2000 meter cube, and the concentration of solids in the flow of aeration tank is 3000. MLSS concentration is 3000 milligram per liter. So MLSS concentration is 3000 milligram per liter. So we can write it as 3 kg per meter cube. If you convert it, it will be 3 kg per meter cube. So here, from this we can know total flow is this much. MLSS concentration in the reaction tank is this much. So we can calculate the solids loading to the clarifier. So total solids loading to the clarifier, how much it will be? Flow is our 400 meter cube per hour into the solid MLSS. So 3 kg per meter cube. So this will come out to be 1200 kg per hour. So this much of the solid is going to the clarifier, secondary clarifier. So now they have asked the surface area of design. So in design clarifier they are given 3.2 kg per meter square per hour. Here we are getting kg per hour. So for surface area of secondary clarifier, it will be, see the unit kg per hour, and design clarifier is 3.2 kg per meter square per hour. If I total solids divided 1200 kg per hour divided by 3.2 kg per meter square per hour, kg per meter square per hour. So it will be 375 meter square. If you divide it, the meter square will go up in numerator. If you divide it, it will be 3.2. This is 3.2, 375 meter square. Is it clear to everyone? Anyone has any doubt in this question? You can type or you can directly ask me. Should I proceed? At least please write in the comment box.
Yes, sir.
Okay. So once again I will explain this, then we will move to the next question. So in this question they are telling a secondary clarifier handles a total flow. First they have mentioned the total flow from the aeration tank. So suppose this is the aeration tank and from there flow is coming to secondary clarifier. They have given the design solid flux and they are telling MLSS concentration of this aeration tank and they are telling amount of flow. So in prime, so amount of flow they have mentioned, total flow. They have mentioned the concentration of solid. The clarifier is required to thicken the solid to 12,000 milligram. Hence, it is designed for a solid flux. They have given the design solid flux also. So from here, we calculated the what is the total solids. How we calculated the total solids? We multiplied the total flow from towards the secondary clarifier into the total MLSS concentration. This 3000 milligram, which is the aeration tank. From there, we got the total solid loading to the clarifier. Now to know get the surface area of secondary clarifier, we divided this total solid loading rate by the design flux, and here we got 375 meter square. So I hope now it is clear. So we will now move to the second question. So a river has a 1000 million liters per day. A river has a flow of 1000 million liters per day. BOD 5 is 5 milligram per liter. Dissolved oxygen level of 8 milligram per liter before receiving wastewater discharge at a location. Then they are saying for the existing environmental conditions, the saturation DO level is 10 milligram per liter in the river. Wastewater discharge of 100 mld with the BOD 5 of 200 milligram per liter, the DO level of 2 milligram per liter falls at that location. Assuming complete mixing of water and river, the immediate DO deficit is. So they are telling a river has a flow this much, BOD 505 dissolved oxygen before receiving the wastewater at a location. For the existing environmental conditions, saturation DO level, the wastewater discharge of this much with the BOD 5 of 200 milligram per liter falls at a location. So basically, a river is flowing like this. From here, wastewater is being discharged at this point. Now, assuming complete the immediate DO deficit is. So this is the wastewater and this is river. So they are telling immediate DO deficit we have to calculate. For immediate DO deficit, we have to first need to know the DO of the mist at this point. Since river is also flowing and wastewater is being discharged over here, what is the DO mix of this at this point? So to calculate the DO mix of that point, now DO mix at that point will be DO of wastewater into flow rate of that wastewater plus DO of the river into flow of the river divided by flow of the wastewater by flow of the river. So I hope. So before now we have to calculate the first DO mix. DO mix will be DO of the wastewater multiplied by flow rate of the wastewater plus DO of the river multiplied by the flow rate of the river divided by summation of wastewater flow rate and the river flow rate. So DO of the wastewater is DO of the wastewater. They have mentioned 2 milligram per liter at the falls at that location. So here it will be 2 into flow rate of the wastewater 1000 mld. So 2 into 100 mld. Sorry, this is 100 mld. 2 into 100 plus DO of the river. So dissolved oxygen level before receiving the wastewater discharge it is 8 milligram per liter. So this is 8. Flow rate of the river is 1000 mld. 8 into 1000 by 100 flow rate of the wastewater by 1000 of the river. So if you calculate it, it will be 200 plus 8000 divided by 1100. So final 8200 divided by 1100. This is 1100. So it will comes out to be 7.45 milligram per liter. So DO of the mix we got 7.45 milligram per liter. Now this is the DO mix. Still we are yet to calculate the DO deficient at that point. So how we will calculate the DO deficient? DO deficient is equals to DO saturation minus DO mix. DO saturated saturation DO level is given as 10 milligram per liter. So here 10 minus the value which we got at the DO mix is 7.45 minus 7.45. So it comes out to be 2.545 milligram per liter. Is it clear? If it is clear, we will proceed. Else, if you have any doubt, you can tell me.
It's clear, sir.
Okay. Okay. So, so we calculate the DO deficit. So, so I will just give a summary of this question. So in this, they have given the flow rate of. They are telling a river is flowing. They have given us the flow rate of the river. They have given the DO value of that river before mixing, and they have given the BOD 5. So in fact, at one point, a wastewater is being discharged, and the data of the wastewater, also characteristics of the wastewater has also been given: BOD 5, DO, and flow. So three parameters of wastewater in the river have been given to us. So they are at the question they are asking what is the DO deficient, immediate DO deficient is. So for calculating the immediate DO deficient, we need to know the DO mix of that point. From then only we can calculate the DO deficient. In the solution, we first calculated the DO mix using the parameters of the wastewater and the river, and from the DO mix, we calculated the DO deficient by subtracting it with the saturation DO level. So moving to our last question. So last question in this is GATE 2022, GATE 2020, set 1. So in this they are talking surface overflow rate of a primary settling tank is 20,000 liters per meter cube per day. Kinematic viscosity of water in the tank is 1.01 into 10 raised to minus 2 centimeter per second, centimeter square per second. Specific gravity of the particle is 2.64. Acceleration due to gravity is 9.81 meter per second square. The minimum diameter of the particle that will be removed with 80% efficiency of the tank is. So the data they have mentioned about, they have given surface overflow rate. They have given the data of surface overflow rate first. Second, they have given the kinematic viscosity. Third, and they have given the specific gravity of the particle. They have given the acceleration due to gravity. Now they are asking the minimum diameter of the particle. What is the minimum diameter of the particle that will be removed with the 80% efficient removed with 80% efficiency of the tank? So before beginning this question, we have to understand the few concepts. what is surface overflow rate. I have already explained all these things in my previous session. However, I will repeat it again. But I suggest you to please go back and look those videos. Already, I have uploaded all the previous sessions in the YouTube. You can go there and you can watch. So, surface overflow rate. When we talk about surface overflow rate, it is defined as it is defined as flow velocity. It is defined as flow velocity at which sedimentation tank sedimentation tank is designed to operate. Designed to operate. So basically, surface overflow rate is defined as a flow velocity at which sedimentation tank is designed to operate. So surface, we denote it by V naught, which is discharge upon surface area. Now, surface overflow rate basically surface surface overflow rate represents the represents the settling velocity settling settling velocity of the of particle settling velocity of particle that can be 100% removed. So surface overflow rate basically represents the settling velocity of particle that can be 100% removed. So in simple terms, if I convey you the meaning of that, in simple terms, suppose v is the settling velocity of the particle. If the settling velocity of the particle is greater than the surface overflow rate, that means 100% removal will occur. 100% removal of particles. If this is a settling velocity of particle, settling velocity. So, just a second. Settling. This is basically settling velocity of the particle Vs. If Vs is less than V naught, then basically V naught is a overflow rate. So then for the to know the percentage of the particle, we have to use this formula. Percentage of the sedimentation tank is given by Vs by V naught into 100. All these concepts I have already explained in the previous classes. So if you are unable to understand, I will request you to please go and watch those lectures. So this efficiency of sedimentation tank is Vs by V naught, where Vs is a settling velocity of the particle, V naught is the overflow rate into 100. Now, in the question, they have given us surface overflow rate is 20,000 liter per meter square per day. So V naught is 20,000 liter per meter square per day. I think it is not 20,000. It might be 2,000. Let me check it one. It is 2,000. It is not 20,000. It is 2,000. So It is 2000 actually. No, sorry, it is 20,000 only. Okay, it is my mistake. It's 20,000 only. So it is given just so it is a 20,000 liters per day. So V naught, if we convert it into the meter per second, 20,000 into 10 raised to a minus 3, 1 meter cube is equals to 1000 liters. So it will be 20,000 meter cube, and 86 divided by 86, so it will come out in the form of meter cube per second. So if you divide 20,000 by 86400, you will get you will get 0.231 into 10 raised to minus 3. So you can write it as 2.314 into 10 raised to minus 4 meter per second. This is minus. Please take care of the sign. 2.314. Now we know the efficiency of the tank is Vs by V naught into 100. Knowing this, the question they have asked, the minimum diameter of the particle that will be removed with 80% efficiency of the tank. Now 80% efficiency, it is given equals to Vs. V naught value came out to be 2.314 into 10 to minus 3, 4. 2.314 into 10 raised to a minus 4 into 100. Whole, this entire thing is, this is 2.314. Now Vs will be 80 divided by 100 into 2.314. This is 2.314 into 10 raised to minus 4. So it will come out to be 1.85 into 10 raised to minus 4 meter per second. So knowing the Vs, we can now calculate the diameter of the particle. So by Stokes law, we know Vs is equals to Gs minus 1 G d square upon 18 mu. So Vs we have found out to be 1.85 to 10 raised to minus 4. 1.85 into 10 raised to a minus 4. In question, Gs to be 2.64, specific gravity minus 1. This is 9.81. This is diameter of the particle. So this is kinematic with 18. Now they have given us the viscosity. Kinematic viscosity comes out to be 1.01 into 10 raised to minus 2 centimeter. So look at the unit, centimeter per second. So we will convert it into meter per second. So 1.01 into 10 raised to minus 2. Since it was in centimeter square per second, to convert it into meter per second, it will be 10 raised to a minus 4. So from there we can calculate the D. The D come out to be 1.446 into 10 raised to the power 5, 10 raised to the power minus 5 meter, which we can also write in the form of 14.46 micrometer. So you can do it like this: 14.46 into 10 raised to the minus 6 meter. So if you write like this, you can take it as a micrometer. So D will be, diameter of the particle will be 14.46 micrometer. So I will. Is it clear to everyone? Do anyone have any doubt? If anyone has any doubt, you can ask. Okay. So this was our last question. However, I will repeat the concept about of this question once again. So in this, they have given the surface over rate of the primary settling tank, and they have given the other data also regarding kinematic viscosity, specific gravity of the settling particle, and the acceleration. They have mentioned what would be the minimum diameter of the particle that will be removed with 80% efficiency of the tank. So to before finding out, we should know the concept of surface overflow rate. As I have mentioned, surface overflow rate is nothing but the flow velocity at which sedimentation tank is designed to operate. Its formula is discharge by surface area. So surface overflow rate represents the settling velocity of particles that can be 100% removed. So in simple terms, if settling velocity of particle is greater than the overflow rate, surface overflow rate, 100% removal of particle occurs. However, if settling velocity of particle is less than the overflow rate, so to know the efficiency of removal, so the formula will be, we have to use this formula to know the efficiency of the sedimentation tank. That is settling velocity divided by overflow rate into 100. So knowing all the since after keeping all the data, so we have first converted the overflow rate in m meter per second form. Then we have used the similar formula from where we have calculated the settling velocity. So after calculating the settling velocity using Stokes law, we have calculated the diameter of the particle. The diameter of the particle came out to be 14.46 micrometer. So this was the today's class. I will be here till 7 o'clock. In case you have any doubts, you can convey me. So
Sir, these videos, recorded video, are available or not?
yes, yes, it is available in the YouTube. I will show you in just a second. It is available in the YouTube. NPTEL. Yeah, see NPTEL Get Environmental Engineering Ayushman. If you click, so session 1, session 2 is also been uploaded. Session 3. Today also I will upload the session 4. So it will be good if you go and watch those videos before attending the next class.
Okay, sir.
So any other doubt?
Thank you, sir.
Yeah, well, so this is all about the concepts. So so before solving the gate question, I will request everyone to understand the basic concept behind the questions. Then you go for solving those questions. So this is all about for today's class. If you want to leave, you can leave, and till 7 I will be here, so that if anyone has any doubt, I can address those questions. Welcome, Trisha.
Thank you, sir.
Yeah, welcome.
Thank you, sir.
Welcome.